Okay, welcome. Today we're going to be talking about water hammer and surge tanks. It's kind of a practical application type issue that we have to be aware of. Just as a reminder, homework number 5 is available now. I solved that last night. It was a fun one. You know, I told you how I was excited because I'd never done a 3-loop one with a spreadsheet before. Yeah, so I did it. I've got the solution if you want to check. It took me, I think I had 6 iterations before it finally converged. I mean, setting up, once you set it up, then you can copy and paste each iteration. So it could have been 6 or 60 and it would have taken essentially the same effort. But it just takes a little bit longer to converge the more complex the network is. The more pipes, the more loops there are, and so on. All right, so that assignment's due next Wednesday. Today, water hammer and surge tanks. And here is a post that I saw related to water hammer. Let me show you what someone wrote, the most expensive mistake they'd ever made. All right, so luckily in this case it was just a bunch of lousy books. It wasn't a beautiful Ferrari that had been damaged. But the idea is that, so as it's being described here, this is not an engineer that's describing it. I think this is just taken off of a message board somewhere. And as they're describing it, they mismatched the order to close the valve and created a water hammer. Creates a backwash up through the pipes. So that's not exactly what a water hammer is. It's not a burst of air. A water hammer is a burst of water. It's not an air hammer, it's a water hammer. So let's talk about that today. There is an interesting video that talks a little bit about water hammer. We'll watch just a couple of moments of that. It's about momentum. The water is moving through the pipe, and it's moving at a certain velocity. It has mass, and it's decelerating very quickly. And so if you look at this valve, it's just a quarter turn of the valve, and it's instantly going from all the way open to all the way closed. Now that's in stark contrast to a gate valve, where the gate valve, as you turn it, the gate is slowly going down and creating a smaller and smaller opening in the pipe. A ball valve can be closed very quickly, and that's why we have, you know, as the water is flowing, suddenly stops, an increase in pressure. So what we're going to do is talk about the conditions that cause water hammer. That illustration, I think, does a great job kind of setting the stage. So let's consider it, in this case, starting with a reservoir, because that's as far as the water hammer will go back towards the reservoir if there's one connected to the pipe system. So initially water is flowing in steady flow conditions, and so the water velocity in the pipe is steady. It's not changing over time. The valve is open. Just the water is flowing freely. And how you'd measure the pressure in the pipe would be the pressure that's caused by a certain depth in the tank. So it's pressurized here, and then the pressure is decreasing in the direction of flow, of course, due to pipe friction. But then what happens is, if we consider a certain volume, just using the control volume approach, and look at what's flowing through these control surfaces and keep track of the momentum in and the momentum out of the control volume. And as a reminder, here's the momentum equation that we saw in fluid mechanics. Remember that the momentum equation said that there's some force required to hold the system steady if there's a difference between the flow in and the flow out in a certain direction. And so if we apply that momentum principle into this control volume, under steady state conditions, the velocity out and the velocity in are the same. And so there isn't any force required to hold that system steady if the flow out and the flow in are the same. But when you suddenly close the valve, there is a temporary difference between the velocity in and the velocity out. In this control volume, the water that's in close proximity to the valve, so the velocity that's out, is lower temporarily. And it's partly because water isn't completely incompressible like we often assume it is. Water is mostly incompressible, and it requires really enormous pressures to compress it. But for a small period of time, there's an imbalance between the velocity in and the velocity out. So just to summarize the process, the water near the valve stops, and there's a buildup of pressure because of the deceleration. And if you remember when we were talking about convective acceleration is acceleration that occurs as a function of position rather than as a function of time. A local acceleration is when velocity is changing over time, but convective acceleration is when velocity changes in the direction of flow. And so the velocity out is less than the velocity in, and so now we have a velocity gradient that's causing a pressure buildup. And so the pressure is really high right up next to that valve that just got closed. And so the pressure wave starts to reflect backwards, and it's reflecting at a speed that's known as celerity. Now, this dashed line that's on the outside of the pipe is meant to illustrate the fact that the pipe begins to swell because of the local accumulation in pressure. Now, as the pipe swells, what that does is it causes more water to flow to the right. Because as the pipe swells and it expands, then more water can enter the part of the pipe that has expanded just very slightly. So when we're doing calculations like this, not only are we keeping track of the compressibility of water, but we also have to have material properties related to what the pipe is made out of. Because we're going to be doing an analysis of how much the pressure increase causes the pipe to expand. And so we'll need to know the thickness of the pipe, the bulk modulus for the pipe, and so the pressure increase is going to cause a swelling of the pipe that doesn't happen permanently. It's just temporarily that the pipe expands. It expands down the line. Like right now you can see that the pressure wave is only part of the way back towards this reservoir. So here the C is representing the speed that that wave travels. And then this delta H is indicating how much extra energy is in the pipe right now. Because initially, as the water was flowing through the pipe, there was head loss, and so the pressure was decreasing in the direction of flow. In other words, this is our energy grade line. That dashed line is the energy grade line. But temporarily, right after the valve is closed, there's more energy in the pipe than there is in the reservoir. And that's part of what drives the wave back towards the reservoir, and part of why there is a surge tank that's needed, is that there's not head loss, but there's head accumulation inside of the pipe. Because the pipe expanded, and so there's some stored energy there. You've just got, it's kind of like when you blow into a balloon. Since there's extra air and extra pressure in that balloon, if you connected that balloon to some sort of a generator, you could extract energy from it. In fact, I think that there have been some cars where they use compressed air as the energy source. And they can't go very far. It's just kind of a novelty technique. But I mean, you've maybe seen toys or things that are run on compressed air. And so temporarily there's more energy in the pipe than there is in the reservoir because of the pipe having expanded. Eventually the pipe expands as much as it's going to expand, and the water is stopped. So the velocity is zero, the pipe is expanded, and there's more energy in the pipe than there is in the reservoir because of that expansion. And so now what happens is that the water starts to flow from the pipe back into the reservoir. So the water's going backwards. And the reason why is that that expanding pipe is beginning to contract again. And so it was holding a little extra water volume. Because the pipe got bigger, there was more water in there than it would normally handle under more ordinary pressures. And so the water velocity, the water is going from the pipe back into the tank, and that shock wave is returning back towards the valve again. And so you can see the C means that the pressure wave is reflected off of the reservoir back towards the valve. Now it's a little bit lower than the first wave was. There are some energy losses each time that shock wave reflects between the valve and the reservoir, but it can make the round trip several times before it's low enough and before the expansion and contraction of the pipe kind of absorbs the energy of that impact. The first video that we watched talked about it in terms of like a certain mass of water that suddenly stopped. It's as though it's an actual hammer that's hitting the valve. So the decreased pressure wave heads back towards the valve, and the wave can reflect. Now what we often want to know is what's the round trip travel time from the valve to the reservoir and back to the valve again. Because the key to preventing this whole process is you have to close the valve slowly. If you close the valve suddenly, then that causes the water hammer. But closing the valve slowly, what it means is that if you close the valve slower than it takes the water to go to the reservoir and back, then the pressure wave won't build up. So it's if you close it faster than that round trip, that the pressure wave will build up. Now here are the applicable equations that we use. The book modulus of elasticity is a physical property of water, and it describes the unit change of volume that water occupies as pressure is applied. And so it's a physical constant that says how much dV, how much the water volume changes when you apply some differential pressure. And we can look up the bulk modulus of elasticity for water at a variety of different temperatures, and it changes slightly based on the pressure conditions. And so what you'll notice is that as the pressure goes up, it requires progressively more and more pressure to increase the how compressed the water is. In the textbook, I'll point out that table 2.3 that's in your book, there's a bit of a typo. These are the bulk modulus units divided by 10 to the 9th, not times 10 to the 9th. So be aware of that. So what you can think of this is for a certain volume, how much the volume decreased relative to itself as a pressure was applied. Now celerity can be estimated by first of all knowing what would be the velocity of water if it's traveling through an infinite extent of water that's not confined by a pipe wall. And the typical velocity of the shock wave just through the ocean where there's no pipes to interfere is about 1440 meters per second. And that's just based on the ratio of the bulk modulus to the density of the water. And we could calculate the same physical constant celerity for other fluids besides water that have different compressibilities and different densities. But this is since we're in hydraulics, water's the fluid that we're most interested in usually. And so the theoretical wave celerity we can calculate just based on the physical properties, but then we have to know something about the pipe that the shock wave is traveling through. Now the actual velocity of the pressure wave in a confined pipe is going to depend on the theoretical wave celerity if it wasn't in a pipe. But then in the denominator of this ratio, things like the pipe modulus, the diameter of the pipe, the thickness of the pipe, and so the physical environment that the shock wave is traveling through becomes an important parameter as well. And so in table 8.6 of your book, it has the modulus of elasticity for a variety of different pipe materials. Some of them are soft, like lead. And so if you're using lead, number one, that's not so great for environmental and health reasons. But then also, because it's so soft, it can expand and contract really easily. And so if there is a a water hammer in a lead pipe system, it's going to be a lot more serious of a water hammer because more water is able to enter into the expanded pipe, and when it contracts there's going to be an even greater volume of water that's traveling back towards the reservoir. Here is the travel time that I was mentioning about. If we know the length of the pipe, and if we want to know the round-trip travel time, then we would double the physical length of the pipe and divide it by the speed at which the wave is traveling. And so C is the actual celerity in the pipe. It's not the theoretical celerity through a fluid of infinite extent. It's the travel time that takes into account what kind of pipe material it's in. And if we want to know the maximum pressure that could accumulate due to this shock wave effect of the water hammer, we'd need to know the initial velocity, the celerity, and the density of the fluid. So the worst case is if you close the valve faster than the round-trip travel time. And if you close the valve more slowly than that, it's not that there isn't going to be any pressure increase. It's just that the pressure increase is less than it otherwise would be. And we have equations that we can use to calculate the pressure increase when you're closing the valve longer than the T sub L. But this delta P formula is the pressure that accumulates if you close the valve faster than the round-trip travel time. All right, so to get some experience using these equations, let's work this problem with traditional units, where we know the physical length of the pipe, its diameter and thickness. Here is the pipe material modulus, and then we've got the physical properties of the water, the bulk modulus, the density of the water, and we want to know what pressure increase are we going to see, the delta P, if the valve is closed instantaneously. And whether it's closed instantaneously or just less than this maximum travel time, then it has the same effect. I've kind of laid the equations out in the order that you'll need to substitute them, starting with the average velocity, then the theoretical wave celerity, then the celerity in the pipe, and so on. Let me just interrupt with a brief reminder about units. So here in the theoretical wave celerity, what you're going to want for the E sub V is to convert the given pounds per square inch into pounds per square foot. So of course you'll have to multiply by 144 to get it from pounds per square inch into pounds per square foot. But then the density, you can leave that as slugs per cubic foot. And the reason why that's going to ultimately work out is that a slug multiplied by a foot per second squared, so a unit of acceleration is a pound of force. And so we have in the numerator the pounds that we're talking about in PSI. You could convert that from pounds into slug multiplied by foot per second squared, and you may be wondering, where do we get a velocity? You know, the time units in this theoretical wave celerity, because it's ultimately going to give us how many feet per second the wave is traveling at. So those seconds come from substituting in slug multiplied by foot per second squared in place of the pounds. So you don't have to manually do all those units conversions. Just what you do need to have is the E sub V in pounds per square foot. Pounds per square foot, and then the density slug per cubic foot.
convert your epsilon? I did inches to feet.
Yeah, like so you can root it. Okay. I just forgot.
You don't necessarily have to change the pipe diameter and the pipe thickness into feet because it's going to be a ratio. You could leave both as inches, but you can't have one as inches and one as feet. And then the same thing is true of the bulk modulus of elasticity and the compressibility, that you can leave those both as PSI. You don't have to change those to pounds per square foot, just so long as the units are the same in the numerator and the denominator of this ratio.
Yeah, but ideally if we converted each of those values, it still should be the same.
It will. So is this a lot of pressure, 407 psi? Yeah, that's a lot. That's about 4 times normal. 100 psi would be maybe on the high side of what you'd expect to see in a municipal network. And so 400 psi is probably going to cause fittings to break or a water heater to explode. It seems like water heaters are maybe the weak link sometimes when pressure gets too high in a network. So the time, minimum time to close, 0.91 seconds. Need to leave it up a little bit longer. Got it?
Because he just went ahead and did the calc since it was 2,000 feet. It's 2 times 2,000.
So your homework assignment has a problem that's pretty similar to this one. Just asks you to figure out, I think, the pressure increase, the minimum close time. So you'll apply the same technique for that homework problem. If you're closing the valve in longer than the minimum time, our book identifies this empirical equation that kind of estimates what the pressure increase would be. We won't work an example, but you calculate this factor that has to do with the initial velocity, the valve closure time, and so it's kind of going to be a reduced pressure, but it still could be enough to cause trouble. And so there are a lot of, in really high value systems like in a water treatment plant, there will sometimes be computer controlled valves that on a programming basis will close the valve really slowly so that an operator wouldn't manually close it too quickly. And of course, you got to, in the animation we watched, they showed you in kind of a residential setting what could be used as a shock absorber to reduce the effect of the water hammer. But another approach is to put in a surge tank. And what the surge tank would do is, rather than having that effect where the pipe is expanding because of the increase in pressure, a surge tank would allow the water level to rise some height inside of an open to the atmosphere tank. It could be also enclosed, but the gas above it would be compressing, and so it would maybe not have exactly the same effect if it's open to the atmosphere. But our book has this formula for the maximum height of a surge tank that's required. And what it is looking at the amount of water that you expect to have accumulate inside of the surge tank. And so it has to do with the diameter of the tank and therefore the ratio of the cross-sectional area of the tank to the area of the pipe. And so you know that the extra water has to go somewhere. And so what we're saying is if you put it in the tank, then the pressure doesn't build up and there won't be the same catastrophic damage. So in this example, let's assume that we have the same 2,000 foot long system, and it's a 4-inch diameter pipe, and we know the initial flow velocity. That was the velocity that was calculated in the last example. But what diameter of surge tank would be needed if we were going to allow the surge depth to be 1 foot? So in other words, if that's the limit that we could tolerate, then what cross-sectional area of the tank is needed? And then once you know the cross-sectional area of the tank, calculate the diameter of the tank, assuming that it's circular. So you'll be solving for A sub t. So we get the area of the pipe, and rearranging, instead of having a surge depth being the unknown, if we say that the surge depth limit is 1 foot, and what we want to know is how big of a tank is required if we're going to allow the water level to fluctuate 1 foot of depth. Then the cross-sectional area that's needed, 256 square feet, is pretty large. That means that we would need a surge tank with an 18-foot diameter. So this is a really long run of pipe, 2,000 feet, that we're trying to protect with the surge tank. And so it's just going to be a certain volume of water that's going to be going up and down in the surge tank. And so it either is going to be a tall surge tank or a wide one. There's a certain volume of water that has to be accommodated during that surge in order to prevent damage. And so it's going to be just kind of balancing out the design considerations. And if we tolerate only a height difference of 1 foot, then we get this really excessively large diameter of 18 feet. But that's to give you a sense of the countermeasures that can be used to mitigate the water hammer. Any questions on this calculation? All right, so be sure and close that valve slowly. That's the take-home message. Homework 5 is available now. It's due on Wednesday. Hope you have a nice weekend. I'll see you Monday.